Hello, my project is titled Low-Cost Deep Learning Solutions for Early Detection of Lettuce Stress in Indoor Farms. Indoor farming is a growing sector and has gained significant investment and attention, becoming a solution to provide food security for urban areas. As the sector increases in size, there currently remains no viable solution to automatically alert growers to vegetation stress in a greenhouse. If a system could provide warnings to crop stress before it is visible to the naked eye, it could have far-reaching impacts. Common disorders encountered in a greenhouse include water stress, nutrient deficiencies, pesticide damage, pest damage, and heat shock. Last year, I experimented with RGB imagery. The system could detect stress when symptoms start to appear for lettuce crops, and could be useful for recovering some of the yield in the event of a catastrophic failure. The project placed first at the Virginia State Science Fair. Here, I provide a solution to predict crop health maps which indicate regions of stress. Development took place at True Farms. This is a commercial greenhouse that is managed by my family, and I realized the need for this product while working shifts at the family farm. To create a viable solution this year, I chose to employ full-spectrum converted cameras. With the blue IR filter, the camera captures both blue light and near-infrared light. The cameras are affordable, costing $160 if conversions are done manually. The blue NDVI index attempted to evaluate the health condition of butter lettuce heads. It could not detect a decline in crop health because there is not a consistent decrease in the coloration. Due to the failure of the NDVI index, there is the opportunity to employ state-of-the-art deep learning techniques to achieve better results. State-of-the-art deep learning techniques can potentially outperform vegetation indexes because they identify stress based on a plant's appearance that mimics human behavior. I collected a diverse data set to train our deep learning models. Water deficits were administered every week throughout the crop's growth cycle to build the data set. Labeling data and machine learning is time-consuming. To reduce the time spent labeling, I use an algorithm that employs the blue NDVI index and RecLabel software to label all of the stressed crops with either polygons or boxes. And with this technique, I was able to create masks for the whole dataset within 2 hours. To train segmentation neural networks, I used a Python deep learning library called PyTorch, along with GPUs available on Google Cloud. PyTorch is one of the most used deep learning frameworks in academia. When training the segmentation neural networks, I do not explicitly program the network to detect features of the crops, such as its color or shape, to predict stress. Instead, by training, the network learns features automatically to predict stress. A novel time series technique allows the model to exploit features regarding the crop's response to stress. For example, if a section of the growing area starts to experience water supply issues, the crop's leaves will move slightly over the period of an hour, indicating that plant cells are losing turgidity. A novel forecasting technique allows the model to predict the growing area's health in the future. In other words, the model is forecasting the crop's health, becoming a predictive model. Figure 8 demonstrates how this is accomplished. Our method was evaluated on the mean Dice coefficient. The Dice coefficient compares the overlap between two regions, specifically the predicted regions of stress and the true regions of stress. Water deficits were administered throughout the growing phases of lettuce. To avoid falsely high performances, the training and validation sets were split so that neither contained the same heads of bib lettuce. Table 2 demonstrates that our method predicts stress not visible to the naked eye for the validation set. Symptoms start to appear 23 hours after the water deficit was administered, yet our method detects it 17 hours after. Our trained model was then deployed to have a comprehensive understanding of its performance. It predicted crop health maps for data it had not been trained or tuned to. The camera collected data for a different plant canopy undergoing a new growth cycle. We administered water deficits at different times and at different locations than the training or validation sets. Our table indicates that symptoms appeared 23 hours after the treatment, but symptoms likely appeared sooner, but data could not be collected until then because it was dark. Table 5 indicates that our method detected water deficits well before symptoms appear. However, it did perform poorly for one image at hour 5. To test if our method performed well on other types of stresses, I administered a treatment to cause pesticide damage. We sprayed 1 row of lettuce heads with high doses of potassium bicarbonate, or known as green cure. After 65 hours, symptoms, which included burning, were visible. This treatment could only be administered once because treated lettuce heads must be discarded. Thus, to assess our method, it was trained on half of the image and was validated on the other half containing different lettuce heads. Training and validation sets contain unique sets of lettuce heads, so this method is reasonable to assess our model. Table 6 demonstrates that our method detected pesticide stress before symptoms appeared. Figure 9 demonstrates that our method performs better when Bibb lettuce is at its beginning of its growth cycle. Figure 10 demonstrates crop health maps predicted by our method. Although our method does not perfectly segment each plant, it does consistently label the majority of pixels belonging to stress as red. In this research, I developed a method that predicts crop health maps for lettuce crops based on converted full-spectrum infrared imagery. Our method can signal to early warnings of stress in lettuce crops before it becomes visible. The system could have significant implications for indoor operations. It could help growers improve their business's profitability by minimizing the crop yield loss and by ensuring that the plant's flavor or quality remains unchanged from long periods from stress durations. Thank you for listening to my presentation.